EasyCAN Troubleshooting. Hello again, my dear subscribers. I am pleased to share with you the 5th edition of the Mech newsletter. This month we will cover CAN bus, which stands for Controller Area Network. In case you are new to the concept and were perhaps a little unsure what exactly CAN stands for. As many of my regular readers will know, my writing focuses on breaking down complex concepts into an easier to understand form. This approach saves time by eliminating unnecessary information that can divert attention from the main task at hand. Understanding the concept rather than the in-depth nuances and troubleshooting CAN when necessary. This edition will break down only the electrical concepts of the CAN bus and not the individual breakdown of how messages are formed. However, I have included a short introduction to how messages are formed, and it might be worth understanding some basics before diving into the how to fix it stage. The start of a new evolution in automotive design. CAN bus, short for Controller Area Network Bus, is a communication protocol and bus standard used in the automotive industry for interconnecting different electronic control units within a vehicle. CAN bus was first developed by Bosch in the 1980s, primarily for use in automobiles to replace the previously used point-to-point wiring systems that were expensive and, at times, unreliable. It was designed to allow multiple ECUs to communicate with each other over a single two-wire bus, reducing the amount of wiring required and improving the reliability and flexibility of the system. The first vehicle to feature CAN bus was the Mercedes-Benz W140 in 1991. Since then, most manufacturers have adopted CAN as it reduces the miles of wiring previously required to carry signals from control unit to control unit. This in itself not only reduces complexity and cost, but also frees up car designers' compromises when designing interior trim, for example, as no longer are trims required to hide huge, cumbersome wiring harnesses. In fact, if you think about it, to feature the equipment level found in a high-end luxury car these days, the wiring harness would be so radically thick that the cost, complexity, and size would make where we are today a non-reality. So, we have a lot to thank Bosch for, don't we? Since its introduction, CAN bus has become a widely adopted standard in the automotive industry and is also used in other industries, including aerospace, industrial automation, and medical equipment. Today, it is the most widely used vehicle bus standard in the world, and newer versions of the protocol continue to be developed and implemented to meet the evolving needs of modern vehicle systems. A CAN bus frame, also known as a CAN message, is the basic unit of data transmission on a controller area network. The frame is composed of several components, including Start of Frame SOF, a single dominant bit that marks the start of a CAN frame transmission. Identifier, a unique 11-bit or 29-bit code that identifies the message's source, destination, and priority. Remote Transmission Request, RTR, a bit that indicates whether the message is a data frame or a request for data. Data Length Code, DLC, a 4-bit field that indicates the number of bytes in the data field. Data field, a variable length field that contains the actual data being transmitted with a maximum size of 8 bytes. Cyclic redundancy check, CRC, a 15-bit or 17-bit code that provides error detection and ensures the integrity of the transmitted data. End of frame, EOF, a sequence of 7 recessive bits that marks the end of the CAN frame. The CAN bus frame structure allows for efficient, reliable communication between multiple electronic control units in a vehicle or other complex systems. The CAN bus protocol is widely used in the automotive industry as well as in industrial automation, medical devices, and other applications. In the image below, what does this frame consist of? In a car, multiple electronic control units, ECUs, are connected on a controller area network bus, allowing them to communicate and work together. Each control unit is responsible for a specific set of functions within the car, such as the engine control unit, known as the ECU, transmission control unit, known as the TCU, airbag control unit, and so on. Some manufacturers use multiple dedicated buses, whereas other manufacturers use less complex single buses. An example of complexity and usage of multiple bus types can be found in BMW vehicles, of which the author is experienced in working with. Common CAN types include KCAN, body data bus, PTCAN, powertrain data bus, LOCAN, sub data bus, FCAN, chassis data bus. In addition to this, there are also other bus types than CAN, such as FlexRay, ByteFlight, MOST, and Ethernet. All of these different buses cannot directly work together as a team, and in such cases they need to go through a central gateway device which acts as a translator that allows different bus signals to be understood and interpreted in order that the vehicle operates as one entity seamlessly. A gateway unit is what exactly? An automotive gateway unit is an electronic component that acts as a bridge between different networks or communication protocols within a vehicle. It allows for communication between different electronic control units that may use different communication protocols or networks, enabling them to exchange information and work together. The gateway unit is typically located within the vehicle's network architecture and is responsible for routing messages between different communication buses, such as CAN, LIN, and FlexRay. It also performs data filtering, protocol conversion, and message translation, ensuring that each ECU receives only the relevant information it needs. Automotive gateway units play a critical role in modern vehicles, which have become increasingly complex with multiple ECUs and various communication protocols. They help to improve the efficiency, safety, and performance of vehicles by enabling different systems to work together seamlessly. Some common examples of systems that may be connected through an automotive gateway unit include the engine control unit, transmission control unit, airbag control unit, and body control module. The gateway unit may also be connected to external networks such as Wi-Fi, Bluetooth, or cellular networks to enable features like remote diagnostics, over-the-air updates, and vehicle tracking. An example of CAN bus in operation may be, for example, when a driver inputs a command through the car's various controls, such as pressing the accelerator pedal or turning on the headlights, the corresponding control unit receives the input and sends a signal through the CAN bus to the other relevant control units. For example, pressing the accelerator pedal sends a signal to the engine control unit, which then adjusts the engine's performance accordingly, and then sends a signal to the transmission control unit to optimize gear shifting. This communication between the control units is bidirectional, meaning that they can also receive information from each other. For example, the ABS control unit can receive wheel speed information from the wheel speed sensors and send this information to the engine control unit, which can then adjust engine power to optimize traction. It is, however, worth mentioning that other control units do not directly communicate with each other. Rather, the ECUs connected to the same CAN bus can create and send data, and other control units can receive or ignore this data during normal operations of the vehicle. CAN is like a meeting place full of gossips. Lots of messages are spread about, and some will be utilized and some not. Nodes connected to branch lines can hear all transmissions broadcasted on the network and may react to the most important or interesting messages. There is no way for individual control units to directly communicate one-to-one with each other. In this sense, CAN can be said to be a broadcasting network. Summing up, CAN bus allows for efficient and reliable communication between various control units in the car, ensuring that they work together seamlessly to provide a smooth and safe driving experience. In addition, the standardized nature of the CAN bus protocol makes it easy for manufacturers to integrate new control units and functions into their vehicles. Messages like those examples above are firing around the bus constantly. When we capture an oscilloscope trace of a bus signal, we are capturing a live view of all of these messages, but in a graphical form. Some advanced scopes, such as Pico, can support serial decoding, but they will not tell you what each message corresponds to, as this is secret, manufacturer-only data that is not easy to get hold of. To understand what these messages mean, one would need to sniff the bus laboriously, note down what messages appear where when a certain function is applied. CAN sniffing is very interesting, but goes beyond the scope of this simple article. A lot to take in. Lots to take in, definitely. And this basic explanation is literally a short taste of CAN bus. We can spend all day breaking down CAN messages and how messages are generated, but in practical terms, as fault finders, it is more important to understand what you should be seeing and what perhaps you are not seeing when you are dealing with an active fault, and how you will use a variety of techniques and tools to efficiently and accurately pinpoint and solve a fault in a naughty, badly behaving or non-functioning bus. At the end of the day, usually when fault finding, all we need to be concerned with are several factors. Bus integrity, mainline intact, all nodes responding, 60 ohms resistance, a good, stable scope trace, no active wiring faults, shorts or opens. What sort of faults can appear, and how do I identify them? What sort of diagnostic approach should I choose in order to accurately pinpoint the fault? A good question indeed, But firstly, we should understand that the laws of physics are constant and Ohm's law is also a constant. Though, having said that, there are times when faults are highly sporadic and buried deep within a thick main wiring harness and hard to find. During these sporadic episodes, faults seem to defy the laws of any science, but it is important to remember that usually, when faced with implausible and downright strange readings from our meters or scopes, that the issue is definitely present as a fault and isn't some otherworldly creature that has possessed the vehicle you are working on. Keep in mind the following factors that must be checked and adhered to at all times when accurately taking measurements on a CAN system. Keep your fluke meter or equivalent in good working order, making sure that the test leads and probes are working and have no excessive resistance due to wear, etc. Take a quick probe resistance check before embarking on a CAN testing routine. Usually, the author's fluke meter displays around 0.1 ohms of resistance, probe tip to probe tip, but at times, on worn leads or tips, this resistance can increase dramatically. Left unchecked, this could falsify results, especially if the tip resistance is above 10 ohms. Though this is rare, yes, but it can happen in theory, so check, and check again, especially if the car you are attempting to fix has some weird sporadic fault that means that the resistance value is wildly jumping and is not constant. Understand the wiring diagram. Identify the main line, the terminating resistor locations, and from that understand the branch lines, their nodes, and their location along the main vehicle harness, should you need to strip and carry out deep investigations to isolate problems. Decide whether you will use an oscilloscope or a fluke-type meter. The next part of this newsletter will discuss this in more detail. Remember to disconnect the vehicle's battery, as the resistance will not be static on an active bus. Keeping the battery on is useful only to check the voltage when the bus is in the so-called recessive state. In this state, the bus lines are in a recessive state, meaning that they are both at the same voltage level, typically at a high level due to a pull-up resistor. This is useful to measure the voltage, which on a BMW powertrain CAN is around 2.5 volts low and 2.5 volts high. So what sort of faults are typical on CAN and how to identify them? Usual faults can be split into several categories. Physical control unit failure, for example, a CAN transceiver failure, burnt or water damage control units, a power supply or ground failure to a control unit, a working control unit, but one which pushes out a dominant or corrupted CAN signal due to some hardware issue internally. In these cases, the whole CAN usually fails to work. Wiring failure on the actual CAN main, branch lines, or both. Incorrectly added retrofit, such as a tow bar causing a CAN failure. Again, a dominant signal crashing the whole bus. There are also many other reasons for the CAN bus to fail, but these are the most common. Identifying faults with an ohm meter, such as a fluke, is a good place to start. If the battery is disconnected, in a good bus, no matter where we take a resistance measurement, should result in a value of 60 ohms. This is because at the end of each part of the main line of the bus sits a terminating resistor of 120 ohms each. Two resistors in parallel are divided so that in a circuit, providing both resistors remain within the circuit, the sum would be 60 ohms. If we were to disconnect one resistor, then there would be a reading of 120 ohms. If there were no resistors present, then there would be an infinite resistance. Here is an example PT CAN bus that shows the locations of the resistors and normal resistance values at various points on the bus, main line at each end and one branch line. The above image shows individual examples of what can happen to the CAN bus overall resistance when there are breaks in branch lines or on the main line itself. The diagram is not exhaustive, but gives an idea of what you would be likely to see when testing with a fluke meter using the resistance setting. You can see that on branch lines, any break that separates the branch lines completely but that still remain intact on the control unit would yield an internal resistance of the control unit that they are still connected to. In this case, the EGS or gearbox ECU would return its total internal resistance. If you were to pick a spot further from the break, away from the gearbox ECU, and you had lines still intact to the main line, you would surely find 60 ohms provided that the rest of the bus lines are intact. If the gearbox harness connector was disconnected and the wiring checked, the result would be an infinite resistance, since we are checking and measuring two broken wires that are not connected to the circuit to the gearbox ECU, nor to each other. Because of falsification of resistance values, it is always best to disconnect a branch line from its control unit, then measure across the terminal, back probing if possible, to obtain a circuit value and not a circuit value and the control unit internal resistance value. The above diagram assumes that each scenario would have no other breaks within the bus. For example, the active anti-roll bar harness connector, when disconnected from the control unit and measured, would usually return a value of 60 ohms. However, in this case, there is an open circuit on one of the CAN wires, so the resistance from positive to negative probe on the fluke meter is also open circuit. Since a resistance measurement can only return an actual resistance value from an intact circuit from probe to probe, the result here would be an infinite resistance. The above image shows an example of two scenarios of two separate shorts within the CAN bus lines. When CAN lines short together, the meter will usually display 0 ohms. The same value will happen to show on the display when you take your fluke probes and touch them together. In this scenario, you need to work out why the CAN lines are shorted together. As in the previous paragraph, all CAN diagnosis work should be carried out with the vehicle battery disconnected, and then each control unit in turn should be disconnected so that we measure the circuit and not the control unit on that particular branch line. At times, you might even need to take away a branch line that you suspect a short on by physically cutting it from the main line, since when faced with shorted CAN lines on branch, it will affect the entire bus, even the main lines. So it is imperative to know where the shorted wires are in terms of rough location rather than the actual point of the fault. Later on the isolated line, if it restores, bus function can be checked further by chopping the now isolated wire into sections and then by using a continuity tester until you find the point where there is no continuity. Then it becomes only a matter of saying the issue is between point A and point B, or point C and point D, etc. Thankfully, this is not such a common problem, at least not every day anyway. The same display of 0 ohms will also be displayed if the terminating resistor is shorted in the control unit. In such a case, it is now easy to measure this by disconnecting the suspect control unit. Now disconnected from the bus, the offended shorted control unit resistor is now no longer affecting the rest of the bus, and the resistance should now display 120 ohms along the entire point of the bus branch lines and main line right up to the disconnected faulty control unit harness connector. Shorts to ground usually show more or less the same resistance as a good bus, since the ground has very little resistance anyhow. When shorts to ground are present or suspected, usually confirmed via an oscilloscope trace, the best way to test this is to isolate the part of the circuit suspected as shorting to ground. Checking this by using one probe of a fluke meter to ground and the other to each individual CAN wire in turn will show via continuity check if this part of the circuit is indeed shorting to ground, much the same way as a normal wire touches ground. The CAN can be checked this way too. According to the opinion and experience of the author, shorts to 12 volts are the easiest to detect, as they tend to crash the entire bus due to the dominating effect of 12 volts across the whole bus, and the oscilloscope will show a dominant flat line at the 12 volt mark on the scope axes. With the battery disconnected, continuity testing each wire to 12 volts will work much the same way as when checking for shorts to ground. The video above shows exactly how difficult it can be to chase down a sporadic wiring fault. The vehicle is a BMW i3, and the PT CAN 2 developed a sporadic fault that would shut down the entire car, rendering all information critical for the functioning of the vehicle to be prevented from reaching the bus. The fault was buried deep within the main harness at the area of the rear subframe, next to the shock absorber. There were no external clues, no chafing, and no ways to find out where this break was. To do this, there was a main harness connector in the frunk area, which when disconnected allowed the author to backpin the harness and measure back into the car to determine that the line to the gear selector had measured 120 ohms. This was enough to cut out 3 meters of wiring from the frunk bulkhead to the GWS unit mainline. From this point, the author had inserted a dummy 120 ohm resistor in place of the disconnected GWS, thus maintaining bus integrity and simulating a GWS. By removing sections of the bus and ticking them off as OK, we can save a lot of hassle and stress by narrowing down our search. As it happens, the i3 usually fails in the front left wheel arch. However, in this case, it was perfect, albeit dirty. The P2 CAN 2 mainline looks quite OK on general inspection, but it wasn't. There was indeed a break present. The issue with this break was the time taken to dig into the harness and to actually find the break. The author ended up cutting the main line halfway under the car and added another resistor there. As seen in the video, you will see that the author was registering sporadic values. With resistance of the harness back to the frunk tested, the author had a solid, unchanging 120 ohms at all times. Checking the opposite way to the rear with the EME being the second terminating resistor yielded the same sporadic results as when checking in the trunk at the EME near the rear subframe. At this point, the author knew that around 2 meters of harness needed to be opened and checked until the issue located. This was a good example of how physically chopping a harness to isolate good and bad parts is the only way, as this avoids unraveling all of the wraps of tape on the whole harness, which of course takes hours. Another image shows a different example of a sporadic short to ground which was difficult to locate. A bad scope trace can easily be mistaken as good. The image above shows a distorted K-can image caused by a faulty CAS unit. Note the image above. It shows a K-can signal that operates at 4.3 volts on the high and 0.7 volts on the low. In this image they are not to scale, but that isn't important. What is important is taking a scope sample at any point yielded the same image. The fault codes were aplenty and nothing worked on the K-can. The seat modules had failed to work, along with parking distance control, comfort access, and many more control units on the K-can. Even the audio system controller was not working. This situation is the classic, I have to remove control units one by one from the system. Damn it! This method is carried out until the signal becomes good. This one ended up being a failed CAS, car access system, that had made the K-can signal rounded at the tops when seen on an oscilloscope. By isolating control units and then monitoring for improvements in the CAN signal, one can solve issues relatively quickly. This is the image of the i3 once the PT-CAN2 signal fault was found and repaired. The author ended up cutting out the main harness almost to the extent of 4 meters in length, as the capillary effect of the corrosion had meant that the water had travelled the full length of one CAN wire, causing severe blackening of copper strands. I hope that this edition of Mech was insightful and that it will help you along your career progression in this industry. Until May, keep practicing, keep learning, and stay tuned to the Mech YouTube channel where you can find more content.